So, I want you to picture a meeting room. Maybe it's in Stuttgart or Detroit or Shanghai. It's late 2025.
Right.
And around this table, you have the head of design, who obviously wants the new car to look like some sleek spaceship. You have the head of software, who just wants to push code updates every Tuesday, kind of like it's a smartphone.
Yeah, the Silicon Valley mindset.
Exactly. But then you have this other person sitting there, the person everyone is, frankly, a little terrified of.
Yeah.
The homologation officer.
The one who actually holds the keys to the kingdom, or maybe it's more accurate to say the person holding the padlock.
That is a perfect way to put it, because I've been wading through this massive stack of documentation you sent over for this deep dive, this strategic roadmap for the 2026 automotive landscape. And looking at all these sources, it really hit me. The modern car isn't just a car anymore. It's a software-defined fortress.
It really is. The industry is going through this absolute fundamental identity crisis right now.
And that's our mission today, right? To decode what this fortress actually is. Because we used to judge cars on 0 to 60 times, or how plush the leather seats were. But the moat around this new fortress is made of regulations so incredibly dense, they make tax law look like a comic book.
Well, historically, for 100 years, the core competency of a car manufacturer was mechanical engineering, bending steel, managing internal combustion. But if you look at the 2026 model year requirements, that paradigm is entirely dead.
Dead and buried.
Yeah. Safety has exploded. It's undergone this massive dimensional expansion. It went from just surviving a physical crash to preventing hackers, managing AI hallucinations, ensuring the car works even when silicon chips fail.
Right, it's a matrix now.
It is a multi-dimensional matrix, and that's the core thesis we need to get across. This holistic compliance is the absolute strategic moat. It is the definitive barrier to entry for any car company in 2026. If you have the fastest car with the absolute best battery range, but you can't pass the cyber compliance gate or the AI safety audit,
You essentially have a really expensive driveway ornament.
you have a paperweight. You legally cannot sell a single unit in Europe, Japan, or Korea. Compliance is no longer just a checkbox at the end of R&D. It is the business model.
So, for you listening, to keep us from drowning in all the acronyms, we're going to structure this deep dive using a top-down MECE approach that's mutually exclusive, collectively exhaustive. We are breaking down this fortress on wheels into 7 distinct, non-overlapping pillars.
Starting with the physical world and then aggressively moving into the digital and corporate realms.
Exactly. So Chapter 9.1 is NCEQP, physical safety. 9.2 is functional safety, or system reliability. 9.3 is SOTIF, dealing with perception limits. 9.4 is fail operational capabilities. 9.5 tackles AI intelligence with ISO 8800. 9.6 is digital defense, so cybersecurity. And 9.7 is NIS2, corporate responsibility.
It's a gauntlet.
It really is. So let's just jump right into the first one when everyone thinks they actually understand. Pillar 9.1, NCAPP, the new car assessment program. We all see the little stars on the TV commercials, right? 5 stars is good, 0 stars is really bad.
But the 2026 Euro NCAP protocols are a completely different beast.
Yeah, reading through this, it doesn't look anything like the crash tests I grew up watching on the news.
Because the days of just smashing a car into a concrete block at 40 miles an hour and measuring how much the dummy's chest compressed, I mean, that's just the baseline now. It's table stakes.
Yeah.
The 2026 roadmap has entirely expanded the timeline of a crash.
It's not just the moment of impact anymore.
No. They are obsessed with the golden hour after the crash. Post-crash safety is now a massive core requirement.
The 90-minute rule. I found the specifics on the electrical architecture here totally fascinating and honestly a bit terrifying when you think about the physics involved.
Let's break down the physics of an EV crash. You have this skateboard chassis, right? And inside it is a massive high-voltage battery, 400, maybe 800 volts.
Oh, what energy.
A lethal amount of energy. So in a massive impact, these pyrotechnic fuses blow within milliseconds. They physically sever the connection to the high voltage pack. The goal is to prevent thermal runaway, a battery fire, or electrocuting the first responders when they arrive. So instantly, the car is effectively dead.
Which is what you want. You don't want to be sitting in a live, mangled circuit.
Correct. But here is the massive engineering paradox. The high voltage system is dead, but the car cannot actually be dead. You have all these low-voltage systems. The 12-volt network that runs the electric door latches, the hazard lights, the e-call system that automatically dials emergency services.
And the rule says that 12-volt network has to stay alive.
It must remain fully operational for at least 90 minutes after the high voltage is completely cut off.
But wait, in most cars, the 12-volt battery is shoved right under the hood in the front,
Yeah.
right? Which is exactly where the crumple zone is.
Exactly. And that is the absolute nightmare for packaging engineers right now. If you smash the front of the car into a pole, you are highly likely to obliterate that standard lead acid or lithium-ion 12-volt battery.
So they have to completely redesign where everything goes.
They do. Do you put a secondary backup battery in the rear of the vehicle?
Yeah.
Do you armor the front battery box so it survives like an airplane's black box? Because think about it. If that 12-volt power dies, those sleek, aerodynamic, flush pop-out door handles that everyone loves,
They won't pop out.
they won't present, and the electronic interior latches won't release.
So the fire department shows up, and instead of just opening the door, they have to waste precious minutes getting the jaws of life out just to pry you free.
Precisely. And worse, if the e-call system doesn't have power, it can't transmit your GPS coordinates. It can't send the data packet that tells the dispatcher how severe the G-forces were or how many seatbelts were buckled. You lose that critical golden hour for trauma care.
So getting 5 stars now means proving your electrical wiring can survive the death of the car itself.
Yeah.
That is wild.
And that's just the post-crash timeline. We also have to look at the pre-crash timeline, the active interventions.
Right, the VRU expansion. Vulnerable road users. I noticed the 2026 protocols get incredibly specific about scenarios that frankly seem chaotic.
Well, real-world driving is chaotic. The old tests were incredibly sterile. A foam pedestrian dummy glides out in a perfectly straight line on a track. The car sees it, the car brakes. Easy.
But the new tests are swarm testing.
Yes, swarm scenarios. Imagine you are approaching a complex intersection at night. It's raining. A cyclist is approaching fast from your blind spot on the right, but a pedestrian wearing dark clothes is crossing against the light on your left.
The car has to track both of them simultaneously.
Track them both, calculate their individual trajectories, prioritize the most immediate threat, and execute an emergency braking maneuver without throwing the car into a spin.
That is a staggering amount of compute. I also saw the dooring scenario in the notes. That feels very targeted at dense city driving.
It's a massive issue in European cities especially. You parallel park on a busy street, you reach for the handle to get out. But a cyclist is zooming up from behind at 20 miles an hour. If you throw that door open, they hit it and go flying into traffic.
A very common, very dangerous accident.
Highly lethal. So the 2026 standard dictates that the car needs side-mounted radar or vision sensors that actively monitor that rear blind spot even after the car is parked.
And it gives you a warning.
More than a warning, it actively inhibits the door latch.
Wait, inhibit? Like the car physically refuses to let me out.
Exactly. If the sensor detects an incoming cyclist on a collision course, the electronic latch temporarily locks out. You pull the interior handle and absolutely nothing happens. Maybe a red LED flashes on the door trim or the handle vibrates haptically. It is a momentary lockout to save the cyclist's life.
I can just imagine the irate customer complaints, though. Like, my own car trapped me inside.
Oh, it's a terrifying user experience tightrope for the automakers. But from a strategic compliance perspective, if you don't implement that feature, you lose critical safety points. And you simply cannot achieve an overall 5-star rating without those active safety points.
It's non-negotiable. Which brings me to the last part of NCIP I wanted to touch on, the driver monitoring. Because this goes way beyond those little coffee cup icons that tell you to take a break. This section on impairment and cognitive distraction feels, well, it feels Orwellian.
It does feel invasive, but the regulators argue it has to be. The European General Safety Regulation, the GSR, and the new NCIP frameworks are pushing very aggressively for direct, real-time monitoring. They essentially want the car to know if you are drunk.
How on earth does a car know I'm drunk without making me blow into a breathalyzer?
It's a highly complex fusion of sensor inputs. Now, there are some Tier 1 suppliers developing ambient sensors that can actually sniff ethanol vapor in the cabin air.
Like a chemical nose.
Right. But the much more reliable immediate method is advanced eye-tracking cameras mounted on the steering column or the rear view mirror. Alcohol fundamentally alters saccadic eye movement.
Saccadic movement.
The rapid microscopic ways your eyes dart around to take in visual information. It also delays your pupil dilation response. The infrared camera is constantly watching your pupils. If it sees that your eyes are sluggish, your gaze is fixed in tunnel vision, and your micro-steering inputs are erratic.
The car is basically building a psychological profile on me in real time.
It builds a mathematical confidence score that you are biologically impaired.
And what happens when that score gets too high? When it decides, I've had 3 beers instead of 1.
It executes a safe stop. It won't just beep an annoying chime at you anymore. It takes over. It will activate the hazard lights, smoothly decelerate the vehicle, and actively steer it over to the shoulder of the highway and park.
It revokes my driving privileges.
In real time, yes.
That is a massive shift in liability. The machine is making a biological judgment call on the human.
It is a huge shift. But the statistical data proves that human error is the root cause of over 90% of all fatal accidents. The regulatory logic has shifted. They realize we can't patch the human brain, so we must legally empower the machine to override the human.
Wow. Okay, so that perfectly sets up our next pillar. Because if we're empowering the machine to override the human, that machine better be flawless. Let's move to pillar 9.2, functional safety, ISO 26262.
Ah, the absolute Bible of automotive engineering.
In the MECE structure notes, you describe this pillar as managing the known unknowns, the foundational philosophy being what happens when the system physically breaks. But for someone listening who isn't a silicon chip designer, why is this so insanely expensive? You noted that achieving ASIL D compliance adds like 30% to the development cost.
Because functional safety, or FUSA as we call it in the industry, is the institutionalization of Murphy's Law. We know for an absolute fact that in the physical universe, things break.
Wear and tear.
Wear and tear, sure, but also completely random hardware failures. Cosmic rays, literal radiation particles traveling from deep space, can strike a silicon wafer in your car's computer and flip a microscopic transistor from a 0 to a 1. A resistor can crack from the thermal shock of going from freezing winter air to a hot engine bay.
So ISO 26662 forces you to plan for that exact moment.
It mandates a highly rigid process called HARA, hazard analysis and risk assessment. We have to look at every single electronic function in the vehicle and ask one very dark question. If this specific component breaks right now, does someone die?
And if the answer is yes,
Then that function gets slapped with an ASIL D rating. Automotive Safety Integrity Level D. It is the highest, most stringent categorization possible. We are talking about the electronic steering rack, the brake-by-wire system, airbag deployment.
so how do you protect against a random space laser hitting your steering chip?
You build a fortress of redundancy. To achieve ASIL D, you almost always need hardware redundancy.
Redundancy like having a spare tire in the trunk.
Redundancy, like having a spare brain running in parallel. We use what are called lockstep architectures. Imagine you have 2 separate processor cores on a chip. They are both running the exact same millions of lines of C++ code, line by line, clock cycle by clock cycle, at the exact same time.
Okay.
And sitting right between them is a separate, dedicated comparator circuit. Its only job is to watch the math coming out of both cores. If core A calculates, turn the steering wheel left, and core B calculates, turn the steering wheel left, the comparator says, great, send the signal to the motors.
But if they disagree?
If core A says turn left, but core B says turn right because a cosmic ray just flipped a bit in its memory, the comparator spots that mismatch in microseconds. It intercepts the signal, blocks it, and shuts down that specific system before the car violently veers into oncoming traffic.
That is incredibly resource intensive. You're basically paying for 2 ultra-expensive chips just to do the work of one, just in case one is wrong.
Exactly. You are literally having your total computing efficiency strictly for the sake of safety. And this leads right into the biggest civil war happening in automotive engineering today, the battle over zone architecture.
Right, the whole software-defined vehicle trend, the SDV. This is the idea of ripping out the dozens of little computers all over the car and putting everything onto one massive central supercomputer, right?
Yes, the CEOs love this. They want a Tesla-style centralized architecture. One giant brain. It saves massive amounts of weight from the copper wiring harnesses, and it makes over-the-air updates much easier.
But safety-wise, that sounds like a nightmare. You're putting everything in one basket.
It creates what we call the mixed criticality problem. Think about it. In a central computer, you have the infotainment system, which is probably running a heavily modified version of Android or Linux, and is naturally full of bugs running on the exact same piece of physical silicon as your ASIL anti-lock braking algorithm.
So if my Spotify app freezes up and crashes, does my emergency braking system go down with it?
In a poorly designed system, yes,
Uh,
and people would die. So the ISO 26262 SIS2 solution to this is hypervisors. We have to use virtualization to build concrete walls inside the silicon.
like running a Windows virtual machine on a Mac.
Very similar concept, but with literal life or death stakes. The hypervisor creates strictly partitioned virtual machines. It physically allocates memory addresses and CPU clock cycles in a way that is mathematically enforced by the hardware. We call this achieving freedom from interference, FFI.
Freedom from interference.
Right. Even if the Android partition suffers a catastrophic memory leak, totally panics, and tries to consume 100% of the CPU, the hypervisor acts as an unbreachable firewall. It guarantees that the safety partition still gets its crucial 10 milliseconds of compute time every cycle to check the brake pedal position.
It's like building an impenetrable panic room inside the house, so if the house catches fire, the panic room is completely untouched.
That is exactly it. But mathematically proving that FFI works under all possible stress conditions, that is an engineering nightmare. It takes thousands of hours of validation.
Which is why I imagine they are shifting to this SEOC concept you highlighted. Safety element out of context.
SEOC is the only way the legacy automakers can scale fast enough to survive. Instead of building the entire house from scratch, they are buying pre-certified black boxes.
Bricks that are already certified to be safe.
Right. If you are a Volkswagen or Ford, you generally don't try to write your own safety-critical operating system kernel from scratch. You go to a specialist software vendor like BlackBerry QNX or Vector, and you buy a software kernel that already has an ASIL certificate stamped on it.
You just plug it in.
Well, you treat it as a trusted brick. But here is the catch. You have to prove that you are using the brick exactly as intended. If the vendor's safety manual explicitly says, do not operate this software component if the hardware exceeds 85 degrees Celsius.
And your engineers package the central computer right next to a turbocharger that runs at hundreds of degrees.
Then your ASIL certification is instantly void. The safety element was taken out of context. And you, the automaker, are entirely liable for the consequences.
Wow. Okay, so Pillar 9.2 handles the known hardware failures and code bugs. But what if nothing breaks? What if the silicon is flawless, the code executes exactly as written without a single glitch, and the car still makes a decision that kills someone?
Now you are stepping into the Phantom Menace, Pillar 9.3, SOTIF.
ISO 21448, safety of the intended function. You call this the existential crisis of modern AI vehicles.
It is the single hardest problem in autonomy, because traditional functional safety assumes that danger only comes from a failure. SOTIF deals with the terrifying reality that the system worked exactly as designed, but the design itself was fundamentally insufficient for the real world.
The phantom braking phenomenon is the classic example here, right? Where a car is cruising down the highway and suddenly slams on the brakes for absolutely no reason.
It is the perfect poster child for SOTIF. Let's dissect a phantom braking event. You are driving down an interstate under a large concrete overpass. It's late afternoon, the sun is setting low on the horizon. This creates extremely long, very dark, hard-edged shadows across the asphalt.
Just a normal driving scenario.
For a human, yes. But your car has a front-facing camera feeding pixels into a pattern recognition algorithm. That algorithm is working perfectly. It hasn't crashed. But it analyzes the high contrast of that dark shadow, compares it to its training data, and classifies that flat shadow on the road as a stationary solid object, a stalled black car.
But the radar sensor in the bumper. Radar waves pass right through a shadow. The radar sees empty, clear road ahead.
Exactly. So deep inside the car's brain, you now have a sensor fusion conflict. The camera is screaming solid object impact imminent. The radar is saying, all clear, keep cruising.
How does the car decide who is right?
The safety logic architecture in most current systems is heavily biased toward conservative action. Better safe than sorry. So the centralized decision matrix sides with the camera, overrides the radar, and commands maximum emergency braking at 70 miles an hour.
Creating a massive hazard for the semi-truck driving right behind you.
Precisely, causing a massive rear-end pileup. Now look at that from an engineering audit perspective. Nothing failed. The camera captured the pixels perfectly, the code evaluated the logic gates perfectly, the brakes actuated perfectly, but the intended function was severely unsafe because the system misunderstood the physics of the environment. That is a critical SOTIF violation.
So how on earth do you engineer a fix for a misunderstanding? You can't just rewrite a single line of code that says, ignore shadows.
No, because then it might ignore a real black car parked in the shade. To fix SOTIF, you have to systematically map out ignorance. We use the SOTIF four-quadrant model. Area 1 is the known safe scenarios. Area 2 is known unsafe things we know the car can't handle, like a blizzard, so we tell it to disengage.
And Area 3.
Area 3 is the unknown unsafe, the absolute blind spots, things we didn't even know we didn't know. The entire regulatory goal of ISO 24248 is to force automakers to shrink Area 3 as much as possible, dragging those scenarios into Area 2 so we can engineer a mitigation.
But the real world has infinite variables. You physically cannot test for every single shadow angle, sun glare, and weirdly shaped truck on the planet.
No, you can't. Toyota actually published a mathematical estimate a few years ago. They calculated that to statistically prove an autonomous system is measurably safer than a human driver, you would have to physically test drive it for 8.8 billion miles.
Billion. With a B.
With a B, that would take a fleet of cars hundreds of years. So the industry is pivoting massively to simulation, synthetic data,
Doing the miles in a video game, essentially.
a massively complex cloud-scale digital twin of the world. Automakers are building exact digital replicas of cities like San Francisco or Munich. They can manipulate the digital sun to shine at every conceivable angle. They can simulate dense fog, heavy rain, sensor noise.
And they test the car's software in that matrix.
Yes. And they purposely inject adversarial attacks. They will simulate a digital stop sign, but digitally place a piece of black duct tape over the word STOP. They run the simulation millions of times to see if the AI gets confused and classifies it as a 45-mile-an-hour speed limit sign.
So they are actively trying to break the car's brain in the simulator.
We are aggressively hunting for triggering conditions. So TIAF is essentially the scientific discipline of validating the absolute limits of a machine's perception. It's forcing the engineers to admit that the machine is not omniscient and legally defining the exact boundaries where its intelligence collapses.
Wow. Okay, so we've covered the hardware breaking, which is functional safety, and the system getting totally confused, which is so tough. Now we need to look at what happens when the car is forced to keep driving regardless. Pillar 9.4, fail operational.
The L3 plus imperative. This is the paradigm shift that fundamentally breaks legacy vehicle architectures.
Because right now, most people driving advanced cars have level 2 systems, right? Things like Tesla Autopilot or GM Super Cruise. And in level 2, the human is the fail-safe.
Exactly. Level 2 is legally defined as a fail-safe system. If the camera gets blinded by the sun or a sensor fails, the system immediately sounds a loud chime, flashes red on the dash, and instantly disengages. The steering wheel goes limp.
And you, the human, have to grab the wheel immediately. Which is terrifying if you were looking at your phone, but legally that's the deal you signed up for. You are the backup.
You are the designated fallback. But the industry is pushing toward Level 3 and Level 4 autonomy. Mercedes-Benz and BMW already have certified Level 3 systems in specific markets. And the core legal promise of Level 3 is that you, the driver, are explicitly allowed to disengage. You can watch a movie on the infotainment screen. You can read a book.
So if the main computer suddenly blows a fuse while I'm watching Netflix at 80 miles an hour,
You cannot expect the human to safely re-engage and take control in 500 milliseconds. Human factors research shows that if a driver is deeply distracted by a screen, it takes them anywhere from 10 to 30 seconds to regain situational awareness. They have to look up, process the environment, realize the car's drifting, and take physical action.
10 to 30 seconds at highway speeds, you've already crashed.
Exactly. Therefore, a Level 3 vehicle cannot just disengage. It must be fail operational. If a critical component dies, the vehicle must have the onboard capability to continue actively steering, actively braking, and actively perceiving the environment for at least that full transition window up to 30 seconds.
It has to drive itself while it's broken.
It has to navigate to a minimal risk condition, an MRC.
How is that even physically possible without a steering column? I saw in your notes that X-by-wire is a requirement here. Steer-by-wire is super controversial right now. No physical metal bar connecting the steering wheel in your hands to the tires on the road.
It makes purists very nervous, but it is the only viable path to true fail operational economy. Because to achieve this, you need total hardware redundancy.
Doubling up on everything.
Everything. In a steer-by-wire system, you have two entirely separate electric motors mounted on the steering rack. You have two completely physically isolated power supply networks. Two separate data communication buses.
So if the primary battery line suddenly shorts out and dies,
The secondary power line instantly takes the load. If the primary steering motor experiences a mechanical seizure and locks up, the system detects it, declutches the dead motor, and the secondary motor overpowers it to steer the car. The availability target for these systems is 99.999%, 5 nines.
A single point of failure legally cannot be allowed to paralyze the vehicle.
Never. And it requires immense state management. Let's go back to the central computer we talked about earlier. Let's say the massive water-cooled NVIDIA or Qualcomm chip doing the complex AI path planning suffers a thermal shutdown, just dies instantly.
The car is suddenly blind.
It would be, but it has a secondary brain, typically a much simpler, highly robust safety microcontroller, maybe an Infineon or NXP chip. It isn't smart enough to navigate you all the way to your destination in city traffic, but it is constantly shadowing the main brain.
So when the main brain dies, the little brain steps in.
It takes seamless control. It commands the redundant steering rack, uses a simplified radar feed, activates the turn signal, checks the blind spot, smoothly crosses 3 lanes of highway traffic, and safely brings the vehicle to a complete stop on the hard shoulder.
It executes the minimal risk maneuver.
Completely autonomously. That is the barrier to entry for level 3.
That sounds astronomically expensive to engineer and build.
Which is exactly why you currently only see true fail operational hardware on flagship $100,000 luxury sedans like the S-Class or the i7. But the regulations will eventually force this tech downward into mass market vehicles.
Okay, let's look closer at the brain making those complex decisions before it breaks. Pillar 9.5, AI intelligence, and the brand new standard, ISOPUS 8800. This was just published in 2024. My first thought when reading the outline was, why do we need a totally separate safety standard just for AI? Doesn't the ISO 26262 standard we talked about cover software bugs?
It covers software, yes, but it covers deterministic software. Traditional software is a series of explicit logic gates programmed by a human. If X happens, then execute Y. It is highly predictable.
Right.
Artificial intelligence, specifically deep neural networks used for machine vision, is probabilistic. It is not programmed, it is trained, it operates on statistics. If X happens, then maybe Y, but probably Z depending on the context.
It's essentially guessing.
Highly educated guessing. Neural networks are black boxes. A human auditor cannot look at a billion-parameter neural net and understand the decision path. The weights and biases inside the network are just a massive, incomprehensible matrix of numbers.
So how on earth do you certify that a black box is safe? How do you homologate a guess?
You have to completely change the engineering paradigm. You stop obsessing over the code itself and you start obsessively auditing the data. ISOPUS 8800 introduces what is known as the data V model.
Treating data as if it were the physical code.
Exactly. In traditional functional safety, we verify engineering requirements against the C++ code. In AI safety, we verify the requirements against the data sets used to train the neural network.
Garbage in, death out.
A literal life or death application of that phrase. The standard legally mandates that you ruthlessly audit your training data set for completeness, statistical representation, and bias. And the massive threat here is what we call out-of-distribution data.
Oh. Out of distribution. Could you give me a real-world example of that?
Sure. Let's say a startup trains its self-driving algorithm entirely in sunny California. The dataset has millions of images of pedestrians, cyclists, and local wildlife, like deer. The neural network becomes incredibly confident at identifying a deer jumping into the road and braking for it.
Okay, makes sense.
But then they export that exact same car with that exact same software to the Australian market. A kangaroo jumps into the road. The neural network has never seen a kangaroo in its training data. The silhouette is entirely different from a deer. The kinetic movement hopping instead of running is entirely foreign to the algorithm's learned physics model.
So the car doesn't see a threat.
It might classify it as a plastic bag blowing in the wind or a strange shadow. It doesn't break. That kangaroo is an out-of-distribution scenario. ISOPUS 8800 requires the manufacturer to legally prove that their dataset thoroughly covers the entire operational design domain they claim to support.
So if you sell in Australia, you better have a statistically significant number of kangaroos in your dataset.
Kangaroos, snowplows in Norway, recumbent bicycles in Amsterdam, the dataset must be exhaustively representative.
But even with a massive dataset, the AI will eventually encounter something weird it's never seen. Can the AI actually know that it's confused?
That is the cutting edge of AI safety right now. Uncertainty, quantification, UQ. We have to mathematically teach the AI to be self-aware of its own ignorance.
Teaching a computer humility?
Essentially, yes. The framework distinguishes between two types of uncertainty. First is aleatoric uncertainty. This is uncertainty caused by noise in the physical environment, heavy rain blocking the camera lens, or blinding sun glare. The AI knows what it's looking at, but the signal is corrupted.
And the second type?
Epistemic uncertainty. This is the dangerous one. This means the object is perfectly in focus, the lighting is great, but the neural network's internal model simply does not know what it is looking at. It lacks the knowledge.
So what does the standard require the AI to do in that situation?
The AI must constantly output a confidence score alongside every single classification it makes. If it sees a stop sign, it doesn't just say stop sign. It outputs stop sign 99.8% confidence.
And if the score is low?
If the AI detects an object but the epistemic confidence score drops below a predefined safety threshold, say unknown object in path, 40% confidence, the overarching assurance case dictates that the system must instantly trigger a deterministic fallback rule.
It stops guessing and defaults to a hard-coded safety rule. Like just hit the brakes.
Exactly. Slow down and increase following distance immediately. The ultimate danger with AI in cars is when the network is confidently wrong.
Like when it's 99% sure that the broadside of a white tractor trailer blocking the highway is actually just a bright, clear sky.
Yes, that exact scenario has caused several highly publicized fatal accidents. So ISO 8800 pushes engineers toward developing causal models. We are trying to force the AI to move beyond mere statistical correlation and begin mapping actual causation.
We need it to explain its reasoning.
We need it to satisfy the assurance case. If we can't mathematically prove why the AI made a decision, we cannot legally trust it with human lives.
Okay, that covers the internal logic and decision-making matrix. Now we have to look outward at the digital threats coming from the outside world. Pillar 9.6, cybersecurity, UN Regulation 155. This isn't just a suggestion anymore, is it?
No, UNR 155 is an absolute hard gate. It is a legal trade barrier. As of July 2024, if a manufacturer wants to sell a new vehicle type in any UNES participating country, which includes the entire European Union, Japan, South Korea, the UK, Australia, they must possess a certified CSMS.
Cybersecurity management system.
Right. And if you fail the CSMS audit, you cannot homologate the vehicle. It doesn't matter if it passes every crash test perfectly, you legally cannot put license plates on it.
So this goes way beyond just hiring some hackers to do a penetration test on the Bluetooth connection before launch.
Oh, massively. Penetration testing is just a tiny fraction of it. UNR 155 mandates a continuous, full lifecycle security posture. You are legally responsible for the digital security of that vehicle from the moment the first line of code is written through its entire time on the road until the day it goes to the scrapyard 15 years later.
How do you even monitor a car for 15 years?
You build a VSOC, a Vehicle Security Operations Center. This is a mandatory requirement now.
I picture a VSOC looking like a military cyber command room.
That's essentially what it is, a massive control room with analysts looking at wall-to-wall monitors, tracking telemetry from millions of connected cars globally in real time. But they aren't looking for mechanical engine faults. They are hunting for digital attack patterns.
Give me a hypothetical. What does a cyber attack on a fleet of cars actually look like on their screens?
It rarely looks like a movie where all the cars suddenly steer off a bridge. It's usually much more subtle. An analyst might notice that exactly 5,000 vehicles in the London area all reported a failed over-the-air infotainment update at the exact same millisecond.
A synchronized failure.
Right. Or maybe the telematics units in a specific 2024 model year SUV suddenly start initiating encrypted data handshakes with an unknown IP address block located in Eastern Europe. The VSOC analysts have minutes to triage that anomaly. Is it just a buggy API update from the weather app? Or is an advanced persistent threat a nation-state actor actively trying to inject ransomware to brick the entire global fleet?
And if they determine it is an attack, they have to respond immediately.
Immediately. Which brings us to the most complex regulatory mechanism in this pillar, the RxS Web of Wine, the Regulation Software Identification Number.
A legal fingerprint for the car's code.
Yes. The days of automakers just silently pushing software updates to fix things in the background are over. If you push an OTA update and that code modification touches any system related to a regulated function, braking, steering, ADS cameras, or emissions, the mathematical hash of that software changes.
The RXSWing changes.
And the moment the RXSWing changes, you potentially void the vehicle's type approval.
Yeah.
You have to meticulously document the update, prove via your CSMS that the new code is secure and doesn't introduce new vulnerabilities, and essentially ask the regulatory authority for permission to update your own fleet.
That is an insane administrative burden. I also noticed a fascinating subpoint here about anti-tampering. You link cybersecurity directly to environmental compliance, like the Euro 7 emissions standards.
They are deeply linked now. For decades, car enthusiasts and tuner shops have modified their vehicles. They plug a laptop into the OBD port, reflash the engine control unit to dump more fuel into the cylinders, bypass the catalytic converters, and get more horsepower.
Sure, people do it all the time.
But under the new cybersecurity framework, the OEM is held legally responsible for preventing that tampering.
So the manufacturer has to actively lock the owner out of their own engine?
Yes, because if an amateur tuner can easily hack the ECU to bypass the NOx emission sensors, it proves that the manufacturer's cybersecurity architecture is fundamentally weak. If you can't protect the emissions data, you can't protect the brakes. So maintaining environmental Euro 7 compliance now requires military-grade cryptographic locks on the engine controllers. It's a completely closed loop of regulation.
It's all connected. Okay. This brings us to the very top of the pyramid. We've gone from the physical car to the code to the data to the hackers. Now we reach the corporate boardroom. Pillar 9.7, NIS2.
The Network and Information Systems Directive 2, this is the hammer. This is the directive that is literally making automotive CEOs lose sleep.
Because of the liability shift, right?
Yeah.
We're moving from the product to the enterprise.
Exactly. Historically, if a major corporation suffered a massive data breach, the playbook was simple. The company paid a GDPR fine out of their legal budget, the chief information security officer got fired as the scapegoat, and the CEO issued a public apology. Business as usual.
But NIS2 changes the target.
It explicitly pierces the corporate veil. It assigns direct, non-delegable responsibility for cybersecurity risk management to the management body.
Meaning the C-suite and the board of directors.
Meaning the CEO, the CFO, and the board members can be held personally liable for gross negligence and cybersecurity oversight.
Personally liable, like paying out of pocket.
Or worse, in some European jurisdictions implementing NIS2, regulatory bodies will have the power to temporarily ban C-level executives from holding management positions if they fail to address known cyber risks.
Wow. You can literally lose your career because you ignored an IT patching report?
It absolutely focuses the mind. It forces cybersecurity out of the basement server room and mandates that it be a standing, heavily scrutinized agenda item at every single board meeting. The executives can no longer legally use the defense, "I didn't understand the tech." They are required to oversee it.
And this liability extends far beyond just their own headquarters, doesn't it?
Yeah.
The notes talk about supply chain liability. Trying to secure an automotive supply chain seems physically impossible. A modern car has, what, 30,000 parts?
Tens of thousands of parts, sourced from thousands of suppliers across 50 different countries. But under NIS2, the automaker is designated as an essential entity. And the directive clearly states that the essential entity is strictly responsible for the security posture of its entire supply chain, Tier 1, Tier 2, down to Tier 3.
So if a small 100-person company in Taiwan that manufactures a basic tire pressure sensor gets hacked,
and that vulnerability creates a digital backdoor that allows the attackers to pivot into the main vehicle network. The OEM is legally on the hook for the breach.
the automaker pays the price for the supplier's weak passwords.
Exactly. So what is happening right now is a massive cascade of audits. Automotive purchasing departments aren't just negotiating the price of aluminum anymore. They are sending aggressive cyber audit teams to evaluate the operational security of mom-and-pop machine shops. They demand to see their encryption key management, their incident response playbooks, their CI/CD pipeline protections.
And if the supplier fails the audit,
If you can't prove your digital security is ironclad, you lose the contract. Period. It is a brutal consolidation of the supply chain.
and then there are the reporting timelines. The incident response window under NIS2 is shockingly short.
It is draconian. If a company experiences a significant cyber incident, they are legally mandated to submit an early warning notification to the National Competent Authority within 24 hours.
24 hours. In a major cyber attack, 24 hours in, the IT team is usually just running around with their hair on fire trying to figure out what server is infected. You might not even know what is happening yet.
Exactly. which is precisely why that VSOC we talked about earlier is absolutely mandatory. You cannot rely on a human opening a log file on Monday morning. You need deeply integrated automated threat detection. Because if you miss that 24-hour early warning window and fail to provide the full incident assessment within 72 hours,
What's the penalty?
the fines scale up to 2% of the company's total global annual turnover.
Global turnover, not profit.
Revenue. For a massive conglomerate like Volkswagen Group or Toyota, a 2% fine equates to billions of dollars. A single mishandled cyber incident can wipe out the R&D budget for an entire fiscal year.
Okay, we need to take a breath and zoom out here. Because looking at this MECE framework, we have truly built an impenetrable fortress today.
A very heavy, very expensive fortress.
Let's synthesize this. We've reinforced the physical structure against chaos with NCIP. We've hardened the internal silicon against random failure with functional safety. We've taught the sensors to scientifically define their own confusion using SOTIV. We've built redundant backup brains to survive a total shutdown with fail operational architecture. We've audited the raw data to tame the probabilistic AI with ISO 8800. We've deployed a global digital shield against hackers with UNR 155. And we've threatened the board of directors with personal ruin to ensure they fund all of it through NIS2.
It is a massive, interlocking, inescapable matrix of defense, and every single layer is mandatory for survival in 2026.
So here's the final overarching question for you. So what this entire deep dive, what does this dense regulatory matrix actually mean for the industry at a macroeconomic level? Is this stifling technological innovation, or is this the only responsible way forward?
It is the ultimate filter. Think back to the last decade. We saw a massive influx of new entrants. Tech companies, smartphone manufacturers, heavily funded Silicon Valley startups. They all looked at the automotive sector and thought they could easily disrupt it because, in their minds, an EV is just a computer on wheels.
Slap a battery on a skateboard, write an app, and you're a car company.
Exactly. But they're hitting a brick wall now because they are learning the hard way that a modern vehicle is not a computer on wheels. It is a highly regulated, lethal weapon on wheels.
The barrier to entry isn't casting the perfect aluminum engine block anymore. It's navigating the paperwork.
It's the assurance case. The ultimate winner of the 2026 global auto market will not necessarily be the company with the sexiest exterior design or the one with a 0 to 60 time of 1.9 seconds. It will be the enterprise that can reliably, profitably navigate this labyrinth of compliance without collapsing under the engineering overhead.
Compliance is the new horsepower.
That is the exact phrase. Compliance is horsepower. It is the definitive strategic moat. If you can master this 7-pillar matrix, your market position is practically untouchable by startups. If you ignore it or try to cut corners, you don't just lose market share, you are legally legislated out of existence.
That is a deeply sobering thought. As consumers, we so often look at safety as the boring part of the dealership brochure, the fine print we skip over to look at the stereo specs. But in reality, what we've unpacked today proves that automotive safety is currently the most sophisticated, high-stakes, multidisciplinary engineering challenge on the planet.
It absolutely is. It is the non-negotiable price of admission for the future of mobility.
Well, I can guarantee that the next time I get into my car and that flush door handle smoothly presents itself to my hand, I am going to be thinking about the 90 minutes of isolated battery life, the hypervisor furiously partitioning memory on the silicon chip, and the VSOC analyst sitting in a dark room halfway across the world staring at a screen just to make sure my steering wheel doesn't get hacked on the way to the grocery store.
As you should. Honestly, when you look at the sheer scale of what has to go right every single millisecond, it is a mathematical miracle of engineering that these vehicles function at all.
I couldn't agree more. Thank you so much for guiding us through the fortress today. It has been an incredibly dense, acronym-heavy, but absolutely revealing deep dive.
My pleasure. It's a complex world, but a necessary one to understand.
And to you listening, thank you for sticking with us through the matrix of regulations. Hopefully, you look at your daily commute a little differently now. Because as we've learned, the car isn't just a vehicle anymore, it's a guardian. Consider this. As these systems get more advanced, with the car monitoring your eyes, your sweat, and the physics of the world around you, we are rapidly approaching a moment where your car actually knows significantly more about your environment and your own biological state than you do. Think about what that means for the future of human liability and insurance. Something to mull over on your drive home. Drive safe out there. Your car is certainly working very, very hard to make sure you do. We'll see you on the next deep dive.